So, what if I told you there's a computer chip out there with a million tiny processors, or neurons, that runs on less power than a hearing aid battery? Seriously, this isn't science fiction, it's a real chip that IBM built. And it's all part of this incredible field called neuromorphic AI. Today, we're going to dive into how building computers that literally think like brains could solve one of the biggest problems in all of technology. To really get why this is such a revolution, we first have to talk about AI's, well, its power problem. I mean, we're in this amazing golden age of AI, right? These models can write code, they can create stunning art, solve incredibly complex problems. But all of that horsepower comes at a massive, massive price. And this quote from the IBM researchers really just nails it. The challenge isn't just about processing more and more data, it's about handling the messy, noisy, chaotic stream of information that the real world throws at us, just like our own senses do every single second. To deal with all this messy, real-world stuff, we've built these absolutely colossal data centers that just guzzle electricity. Did you know that training just one large AI model can have a carbon footprint of hundreds of transatlantic flights? This isn't just an environmental thing. It's a real, fundamental bottleneck that could seriously limit the future of AI. And this slide really paints the perfect picture. On one side, you have our current approach, just brute force computation that needs city-scale power plants to run. And on the other side, the human brain. It does things that are way more complex, and it runs on about 20 watts of power. That's less than a dim light bulb. This mind-blowing efficiency is basically a blueprint for a totally new way to build computers. So that's the big idea, right? What if, instead of just trying to make our current computers faster and faster, we built computers that were designed from the ground up to work like the brain itself? And that is the core concept of neuromorphic computing. It's not about running a simulation of a brain on a regular computer. No, this is about building the hardware, the actual silicon chips, to be structured like a network of neurons. And the key piece of tech that makes it all work is something called a spiking neural network, or an SNN. Okay, so here's the absolute crucial difference. Your laptop, your phone, its processor is clock-driven. It has this constant, steady heartbeat, a clock cycle. And with every single tick of that clock, it's crunching numbers, whether it has anything new to do or not. But neuromorphic systems, they're event-driven. They literally just sit there, using almost zero power until an event, a spike of information arrives. It's the ultimate inefficiency. Only do the work when there's actually work to be done. So how does that actually work at the neuron level? Well, using a model called Loihi, Integrate, and Fire, a little silicon neuron receives these incoming spikes of data. Each spike adds a little bit to its internal electrical charge. If it gets enough input, enough spikes in a short amount of time, its charge crosses a threshold and bam, it fires its own spike out to all the other neurons it's connected to. Then it just resets and waits for the next event. It's so simple but so powerful and unbelievably efficient. Now, this all sounds great in theory, right? But does it actually hold up in the real world? Well, researchers have been building these brain chips for a while now, and the results, they are starting to get seriously impressive. Let's just take one of the biggest names in the game, Intel's Loihi research chip. This single piece of silicon has over 130,000 artificial neurons packed onto it, all interconnected in this mesh that's designed to mimic the brain's parallel structure. This isn't a concept, it's a full-on neuromorphic processor. Okay, so we've got the hardware, but this is the real question, isn't it? The million-dollar question. What's the actual performance gain here? The answer, for certain kinds of tasks, is staggering. In benchmarks where they put Loihi head-to-head with conventional CPUs and GPUs, it has shown up to a 100-fold improvement in energy efficiency. And that is the magic of that event-driven design we were talking about. For jobs that have sparse, real-time data, like processing what a camera or a microphone is picking up, these neuromorphic chips can get the exact same results while using just a tiny, tiny fraction of the power. So where is this advantage actually being used? Well, the applications are pretty much perfect for any device that needs to be smart, fast, and, most importantly, run on a battery. Yeah, we're talking about the next generation of robots and drones that can react instantly to whatever's happening around them. We're talking about smarter driver assistance systems in our cars, tiny, low-power sensors that can monitor factory equipment or run for years inside your smart home. All of these are areas where having real-time intelligence at super low power is an absolute game changer. Okay, get this. This is an absolutely amazing example. Researchers built an algorithm for Loihi that was inspired by our sense of smell. The chip learned how to identify 10 different chemicals after being exposed to each one just once, a single time. That's called one-shot learning, and it's something that conventional AI is really, really bad at. It just shows the potential for these systems to adapt on the fly. And here's another one, this time from robotics. A Loihi-based system controlling a robot arm used over 43 times less power than a similar setup using a GPU. But get this, because of its super fast event-driven processing, it was actually more accurate at the task. Less power and better performance. I mean, that's the dream right there. That is the neuromorphic promise. So if this technology is so amazing, why aren't all of our gadgets running on brain chips already? Well, like with any truly revolutionary tech, the road to getting it everywhere has a few bumps. First off, you can't just program these chips like a normal computer. You need totally new tools, new algorithms, new ways of thinking. Second, to really get the full benefit, the sensors themselves, the cameras and microphones, they also need to become event-based, sending data as spikes instead of big, dense video frames. And then, of course, you've still got hurdles like manufacturing cost and just convincing the entire tech industry to adopt a completely new way of doing things. And this brings us to a really, really important takeaway. Neuromorphic chips are not here to replace the giant GPUs in data centers that are training these massive language models. Those GPUs are powerhouses, and they're optimized for crunching huge, dense batches of data. Neuromorphic chips are specialists. They're designed for super efficient, super fast processing of sparse, real-world data right at the edge, right where the action is happening. You should think of them as partners, not competitors. Look, the journey is really just getting started, but the potential is just undeniable. By taking our inspiration from the most complex and efficient computer we know of, the one that's sitting inside our own heads, we might just be on the edge of a whole new era of intelligent, efficient, and truly autonomous machines. The question isn't really if it's possible anymore, but just how fast this future is going to get here.